This is tutorial 4A, Laplace Transform question Q2c. We are given a transform signal h of t, which has been transformed by Laplace to h of s. And it is a rational function, and now we are interested to look at what is h of s. Look as in we want to visualize h of s. So we are going to plot the magnitude of h of s as well as versus the Fourier transform of h of t. So this is the Fourier transform of h of t. Well, let's plot h of s. So to plot h of s, remember that s is the complex plane. This is the real number. This is 0. This is 1. This is minus 1. So we have the real plane, real line here. And this along this guy is the imaginary line. And the whole surface on the bottom is the complex plane. So for each of these points, we're going to substitute s. And now when we substitute s, it is a, for example, if we substitute here, this point, it will be the real is 1 and the imaginary is minus j. So at this point is 1 minus j. And at this point is 0 minus j. And so on and so forth. So by substituting different s into the above, we can plot the surface. Remember that if we put complex number in, typically complex numbers comes out. But we are plotting the magnitude. So we are taking only the absolute value of this complex number that comes out. Now something very exciting happens when s is equals to 0.9. When s is equals to 0.9 real, then the numerator becomes 0. So look, where is the value s equals to 0.9? It is here, 0.9, and we are interested in plus j equals to 0. So j equals to 0 here. So this point exactly is where the 0 happens. So you can see that on the surface, the whole surface will start to converge and move towards 0. And at exactly real part equals to 0.9, imaginary equals to 0, the function h of s, so h of s equals to 0.9 plus j0 is equals to 0. Now, another exciting things happen when we have s equals to minus 0.2, because when s equals to minus 0.2 plus j0, then the denominator becomes 0. So numerator divided by 0 equals to infinity. So where is minus 0.2? Is exactly here. And so if we start to see this, it will become at this point. And you will realize that at this point, the surface becomes infinity. Now, so you will realize that it is not very easy to visualize this surface at magnitude. Typically, we prefer to visualize it as in its log scale, log magnitude. So the infinity becomes a sharp point, and here is the log scale, and the 0 becomes a negative value along this vertical axis. So now we can visualize it going to the 0 and it goes to the infinity, and there is more resolution between the values from 0 to positive values. So remember, when we are plotting magnitude, there is only absolute magnitude, and the smallest value that absolute magnitude can be is 0. Because we take log, it becomes a negative value. So this is the magnitude plot, and this is the log magnitude plot. So that is the difference. And you can either plot any of them, but the common idea is to plot the log magnitude. Now, where is sigma equals to 0? So when sigma is equals to 0, it is along this blue line here. let us plot the surface along this blue line. It is this red line over here now. This red line that we are seeing is actually h of sigma equals to 0, then omega, j omega equals to from minus infinity to infinity. So this red line that we are seeing now here along this surface actually is from minus 2 to 2 at this moment. This plot is the plot of h j omega, which is the plot of the Fourier transform of ht. I'll give you one more example of the plot between the Laplace h of s versus h of omega. In this example, this x of t is the rectangle pulse. So this x of t is this pulse over here. It has a width of tau, and it is delayed by tau over 2. So we have a pulse, a unit pulse, and remember the unit pulse will produce the sinc function. Well, we can go and take the Laplace transform of this pulse, and the interesting thing is, although we are going from minus infinity to infinity for bilateral, or from 0 to infinity for the unilateral, in this particular case, since the signal only exists from 0 to tau, then we only need to integrate between 0 to tau, and the value of the signal is only 1. So this is a very, very simple integration to do. We get this expression, and finally this is h of, this is x of s, the Laplace transform of x of t. Now we then want to plot this figure. What does this figure look like? Well, remember, as I've said, you just put different values of s, and here as well as here, and then this is the surface. This is the surface of x of s. So again, where's the real? This is the real sigma, this is 0, and this is the imaginary. So this is the surface of h of s, and he's plotting the absolute value, so the magnitude. Now remember, the interesting thing is when we are interested in sigma equals to 0. So we draw the blue line over here. Now I have to color it red, and we extract this red part, and in fact this is very, very similar to the sinc function, and in fact it is exactly, well, it is exactly the magnitude of the sinc function. And then you can see that along here, which is omega, is actually along here, which is the along the imaginary axis s. So this figure is actually this figure and this figure are identical, because this figure in the bottom can be extracted from the top figure. The bottom figure is the Fourier transform of x of t. So now you can again understand the relationship between x of t, x of s, and x of, so this is magnitude of x of j omega. Sometimes we just write x of omega, whichever you prefer. Just read the discussion or the definition of x of j omega or x of omega for your particular Fourier transform. Thank you.